Quantum communication, what is it? Well, we're just the moving of quantum information as encoded in some quantum state from one place to another. So how do we do that? Well, physically, we're going to have to move some sort of quantum particle or quantum system or quantum mode of some sort, physically move it from one place to another. For it to be useful, it will need to be true that if my quantum particle that I'm moving is initially entangled with some other quantum particle, then after the transfer, these two quantum particles need to still be entangled, at least to some extent. If they are no longer entangled, then we can't do anything useful with our communication, with our quantum communication. Quantum communication protocols don't necessarily need you to send entanglement through the channel, but the transfer needs to be able to preserve entanglement in the way I just said. So I'm going to have these overview slides that are really bright, which will hopefully wake you up each time I change topics. So these are the things I'm going to talk about. What the conduit for quantum communication is, the quantum communication channels. Say a bit about that and what the limits currently are for quantum communication. And then I'll talk about how we can go beyond those limits using quantum repeaters, and explain the 3 generations of proposals for quantum repeaters and what the various advantages and disadvantages of them are. And then I'll talk about discrete variables versus continuous variables. And as Michelle mentioned, we have both sorts in our centre, but it's maybe not clear to everybody in the centre what this is about. And then I'll talk briefly at the end about state of the art of quantum repeaters and where we're going. So this won't be a very technical talk. So it's aimed to just give those who don't know a lot about this an idea of what's going on in this space. And please, I'm going to try and leave about 5 minutes for questions at the end, but if you want to stop me and ask questions because you really don't know what's going on, then that's fine as well. So, first thing, quantum communication channels. So, well, before I get to that, I guess we should discuss a little bit about why we would want to do quantum communication. So the sort of most talked about quantum communications is for secure communications. So this is basically about the fact that if you distribute entanglement, then you are basically distributing a random key for which you have you can work out exactly how much information is leaked to an eavesdropper. And obviously to distribute entanglement or the equivalent of distributing entanglement, you need quantum communication. Another possibility is in quantum computing. So this could be just simply that you can't fit all your, silicon-based qubits into a single dilution refrigerator, and you need several of them. But in order to put all those qubits together, you must be able to communicate between these. Or it could be more sophisticated tasks where you're actually thinking about users far away with their own sort of small computers talking to some large central quantum computer. And then finally, there's enhanced sensing. There are sensing protocols in which it is useful to be able to distribute entanglement between faraway locations, and you can enhance sensing or clock synchronization and things like that. Mostly, I'll be talking about the secure communication type protocols. So when I talk about quantum communication channels. I'm just talking about how we move the quantum information around. And I'll always be talking about optical communication channels. So why is that? Well, obviously you want your communication to be as fast as possible. And in vacuum, light travels at the speed of light, so it can't go any faster than that. And also you want low decoherence. You want to be able to coherently transfer your quantum states so that they preserve entanglement, for example. And this is possible with light because light doesn't interact with the environment in a vacuum. And so it's perhaps the lowest decoherence choice. So when I talk about quantum communication or quantum communication channels, I'm always thinking about sending light signals between two different places. So seeing as we're talking about light, then we need to talk about what are the different ways we can encode information into optical states, into quantum optical states. And roughly speaking, you can sort of break it up into these 4 types. So there are single photon qubits, either encoded in polarization, typically, or sometimes time bin. And what we're talking about here is states of a definite energy, 1 photon, but then you use some other degree of freedom to encode the information on them. So the photon is either horizontally polarized or vertically polarized, for example. But of course, you can put it in superpositions. So this is the state of choice for sending discrete quantum information. You're just sending qubits. You can also have coherent or squeeze states. So these are states where you have as well-defined amplitude as you can, but they don't have definite energy. These are the states of choice for sending continuous quantum information. Then we can have more exotic states like CAT or GKP states. So these are kind of hybrid continuous discrete systems in the sense that they're made up of continuous states in a sense, but they encode discrete information. They encode qubits. An advantage to these sorts of states is that they have a kind of built-in error correction, which I'll refer to briefly towards the end. And then the other possibility is field qubits. So this is where the energy state defines the logical state. So the vacuum is 0. A 1-photon state is 1. 2-photon state is 2, etc. And these turn out to have quantum processing power even with just linear optics in a deterministic sense. And as Michelle told you, the centre is looking at all these different types of encoding for various different reasons. Okay, so I told you, okay, we use optics to send our quantum information around, but of course it's not quite as nice as this. There is always going to be some loss on your channel. There may be other imperfections, but I'm going to focus mainly in this talk about the effect of loss on quantum communication. So why is that? Well, terrestrially, typically we are sending things through optical fibres, and optical fibres are not vacuum, made of glass, so there is scattering and absorption loss within the fibres, and other nasty things that can happen. If we use free space at a terrestrial level, then again we've got some scattering from the atmosphere, but we also have temperature gradients in the atmosphere which can cause beam wandering and loss again. Even if we're out in space, communicating perhaps between 2 satellites, then in vacuum, we still have the issue that the beam will spread through diffraction, and unless you want to make your detectors, a football field wide or something, you're not going to catch all the light. And so, again, you're going to suffer from loss. So what does this loss do to our different encodings of quantum information. So for the single photon polarization or time bin qubits, you get erasure errors, meaning that you send your qubit and maybe it doesn't arrive. Okay, so that's one type of error you can have. For coherent states, it's a bit different. The amplitude through the loss just is reduced, and so you end up having a lower signal to noise, and so you make more mistakes when you try to decode the information that you've sent. For the cat states, well, they suffer phase flip errors, and field qubits, well, they suffer amplitude damping. Because they're encoded in energy states, then the higher the energy state, the more rapidly its amplitude decays. And so the whole structure of the superposition gets distorted as it's propagating. So just like to say a little bit about, well, how far can you actually go? What's the sort of the record? So for quantum key distribution, I think this is probably the record still, at about 420 kilometres by the group at the University of Geneva and their collaborators. And this table down the bottom illustrates the issues that occur. So, and if we look up at 250 kilometres, so there's a couple of things to look at. The block time, that's how long it takes to send, one block of information. And we see at 250 kilometres, it takes about 12 minutes. And in the end, after you've extracted your secret random key, you end up with about 5 kilohertz as a key rate. But you see things go drastically bad as you go further and further, simply because you're losing more and more photons, and the loss in a fibre goes exponentially with the length. And so by the time you get to 420 kilometres, it takes you a day to send a block of information, and you end up with a secret key rate, which is less than a bit per second. So it becomes completely impractical. In free space, the record is, I guess, held by the group of Zhanwei Pan in China with the Messius quantum satellite. They did a lot of interesting experiments with this satellite. One of them was to distribute entanglement between two cities in China that were 1,200 kilometres apart. So this was a real hero experiment. You notice, though, that this is the number of counts they got in one go, and it's not very many, maybe 100 or so, 200, something like that. Enough to observe that they definitely had distributed entanglement over this vast distance, but, obviously at the limits of what you can do. Yep.
What was the main limitation for that?
So, well, two things: loss. So there's a very large attenuation here. So very few of the photons that are sent actually get there. And the second is you've only, unlike in a lab experiment where you can sit there for hours on end, the satellite is only in range for a short time. So you've got a very narrow window in which you can actually send your states, your photons. Both of these examples I just gave are for discrete variables, so sending single photon qubits. In the continuous variable domain, there's the AlphaSat experiment run by Max Planck in Erlangen. And there they transferred states from geostationary orbit to Earth, which is 36,000 kilometres. So that's astounding. However, those states were not very quantum. They were thermal states. So there wasn't entanglement distributed there. But nevertheless, it it shows the potential for space-based communications. And there's some commercial interest, mostly in terms of the secure communication side of things. There's many, many companies. I've just put up a few here of historical importance. ID Quantique, Toshiba and MagiQ focus on discrete variables. Quintessence Labs is interesting because it's in Australia. Also, they concentrate on continuous variables, and also they've been a partner of the centre since 2011. Okay, wake up again. Okay, so now we've seen basically what the limits are of quantum communication by just sending light signals. So how might we extend the range of quantum communication? So that's what I want to talk about now. And this is sort of generically called quantum repeaters. So if we have a classical communication channel where we're sending classical signals along, we have a similar problem. There's loss, and after a while, our signals will get too small. So in a classical communication situation, what we do is we break up the channel into smaller segments, and then we place amplifiers in between the segments. So the signal decreases, then we amplify it back up again, it decreases, we amplify it back up again. And we can go much further in that way. So what about in quantum communication? Well, traditionally it's been a lot more difficult than that. So again, we break things up into smaller segments, but then what we do is we distribute entanglement between those segments, and the segments are short enough so that the entanglement doesn't get completely destroyed, but it does get messed up a bit. So then we have to do something called purification, in which we make the entanglement better. I'll say more about this in a moment. And then we can do something called entanglement swapping, which takes the entanglement between the segments and brings it out to be between between Alice and Bob. But then that messes things up a bit more, and we have to do more purification. The thing to notice about this is all the communication that's going on. Continually sending signals backwards and forwards, saying, you know, this worked, this didn't work, fix this up, do this. So this tends to be quite slow. There is another way, and that is by using quantum error correction. And now things look much more like the amplifier picture. We go through some decoherence or loss, we fix it up at an error correction station, go through some more, fix it up again, etc. The only trouble here is that in order to be able to fix it up, now you have to error encode your qubits. You can't just send your single photon qubits, you have to send some multi-photon state which has an error correction ability. So these are what are called generation 1 and generation 3, and I'm going to work through the 3 generations now in a little bit more detail to give you a bit of a better idea of what exactly goes on. So generation 1 is this distributing of entanglement situation. So what you do in the beginning is you distribute a whole bunch of pairs of entanglement between all your nodes, and we go through the loss in between. So things have got messed up with the entanglement, so now we have to purify. And purification is like a filtering process. We pick out the pairs that happen to be good and throw away the ones that weren't. So inevitably, we reduce the amount of pairs we have and increase the average entanglement of those that are left. So then we do this entanglement swapping, which moves it out to being further, the entanglement being over further distance. But that messes things up again, so we have to do purification again. We lose more of our particles. And we go on and on like this, and eventually we get pure particles, hopefully, between the two ends. But you can see that you're going to start off with a lot of particles and then end up with not many. And it's kind of worse than that. The purification protocol itself is something that is iterative. So you run it once, it gets a little bit better, and then you put the ones that were better into it again. They reduce in number again, and they get a bit better, etc. So all the time, you're having to communicate backwards and forwards. And this means that this protocol is slow because of all this communication backwards and forwards. And it's also requires very good quantum memories because you have to hold all your qubits at the local stations while you're doing all this communication backwards and forwards. On the other hand, purification is pretty forgiving. You can start with pretty bad qubits that have gone through a lot of loss or a lot of decoherence and still be able to boost them up. And so the repeater stations can be quite a long way apart. So I'll go very quickly through generation 2 because people don't really use it anymore, but it's kind of a stepping stone. What happens here is we replace our physical qubits with logical qubits which are encoded against errors. And then instead of doing purification, we can do error correction. And what this means is that there's far less communication required. And this makes things faster and reduces the requirements on the quantum memory. But now quantum error correction isn't as forgiving as purification. And so we have to bring the repeater stations in closer. Finally, there's generation 3. So this is where we do everything with error correction. So we start off with error-corrected qubits. Our repeater stations are now error correction stations, which are basically just teleporters. All the classical communication travels in the one direction along with the quantum information. So in the end, there's no communication backwards and forwards. And so this is the fastest system. It's as fast as you can send the qubits, basically. In principle, there are no quantum memory requirements. However, now the loss between the repeater stations absolutely cannot be more than 50% because of the no cloning theorem, which says error correction cannot work if you have more than 50% loss. And then if you've got other errors, then that's going to become even more stringent. I'll just quickly go through an example to show you the advantages and disadvantages of this generation 3 type protocol. So this is a protocol I was involved in, so I know a bit about it. And it's an all-optical device in the sense that everything's encoded in photons and there are no atom memories or anything like that sitting around. Everything is just done with beam splitters and photon counters. Looks a bit like this. The main thing is that the measurement done in here is a big concatenated device, but in the end it all just comes down to beam splitters and photon counters. So that's nice. The other nice thing is that this device can, get you 70 kilohertz rates over 10,000 kilometres, which is, the sort of thing you'd like to be able to do with quantum information with good state quality. So that's the good news. So the bad news is, in order to get into this regime, all this stuff here has to work with an efficiency, in the mid to high 90s. Your repeater stations are only allowed to be, 1 to 1.5 kilometres apart. So that's pretty bad. That's over 10,000 kilometres. That's a lot of repeater stations. And the code size, so the number of photons in each logical qubit is in the hundreds. So in principle, it's very powerful, but technologically very challenging. Okay, so now I'd just like to discuss a little bit the differences between discrete variables versus continuous variables. What time did I start? 15, okay. Okay, and try to tease out what the various advantages and disadvantages are, and what we're doing in the centre. Okay, so I'm just going to zero in on these two types of encoding: single photon qubits, say in polarization, and continuous variable states like coherent states or squeeze states. So the discrete case, we have single photon states, and there's some degree of freedom like the polarization, which encodes the information. And when we measure, we need to count those individual photons. So we have to know if there's a photon there or not. And we can use a polarizing beam splitter to find out whether that photon is in the horizontal or the vertical state, say. And so this is really there's only two outcomes. If I've got just exactly one photon here, it either goes to the horizontal detector or the vertical detector, and so it's a discrete thing. Then there's continuous variables. So now this, as I said, is a state that has an amplitude, a complex amplitude, and what we measure is either the real or the imaginary parts of it. And the way we do that is now with a photodetector, which doesn't resolve single photons, but resolves a macroscopic photocurrent, and we introduce a bright local oscillator, which is a phase reference. Now, if our signal is in phase with that local oscillator, then we see a signal at our detectors. If it's out of phase with the local oscillator, then we don't see a signal. So we have a phase-sensitive detection system. And of course, the amplitude is not 1 or 0. The amplitude can be anything you like, so that's why it's a continuous variable. I can get a continuous range of outputs from this detector. Now, if we're just talking about loss, there's a very nice thing about the discrete variable case, and that is that there is no entanglement between what goes out to the environment and what goes on to our receiver Bob. So, indeed, if a photon gets to Bob, then we know it did not get to the environment. Okay? So, if we use something called post-selection, which is where Bob only worries about the results where he actually got a click, he actually got a photon arriving, then he can screen out the loss effectively. Now, the rate goes down, but things like entanglement and stuff like that are not disturbed. So this is a powerful feature of the discrete variable setup. Now, for continuous variables, if we send coherent states, it's also true that there is no entanglement between the environment and our receiver. However, there are classical correlations. And so it's not quite as simple. So there is information leaking. It's not quantum information in some sense, but it's still classical information is leaking. And in QKD type protocols and things, you have to do something about that. You have to work a lot harder to get rid of it than what you do in this case. So that's an advantage, I guess, in discrete variables. Now let's talk about the sources. So the source for continuous variables is something called a two-mode squeezer. It produces an entangled state via a nonlinear crystal. And the relationship between these continuous variable states and this entanglement is that if on one arm I make a detection like this, called heterodyne detection, a continuous measurement, continuous variable measurement, then I will project the other state into one of these coherent states. And this is a deterministic process in the sense that I always get a coherent state here. The amplitude of that state randomly varies, but is told to me by what the result of this heterodyne detection is. What's more, I can also produce coherent states deterministically just using a laser. So I have both a source, a deterministic source of coherent states, or indeed squeeze states, and I also have an entanglement, a type of entanglement which is exactly compatible with that. Okay, so now discrete variables. Well, the source of choice is actually the same thing. It's a two-mode squeezer. It's run in a very different regime, and also we need to introduce a polarisation or time-bin degree of freedom, which makes it a bit more complicated. But at the heart of it, it's just a two-mode squeezer again. The relationship now is about what the measurement I make is. So now, instead of doing a continuous measurement, I make a discrete measurement. I do photon counting on this output. And if I get, in some polarisation basis, one photon here, then I will project the other mode into a single photon in a known polarisation. So again, I get the fundamental states that I'm trying to send. So again, this is the relationship. But there's a difference. For the continuous variables, it was deterministic. Every measurement led to a coherent state. In this case, it's non-deterministic because one possibility is, and in fact a highly likely possibility, is that I detect nothing. I just get the vacuum. And that means I've just got the vacuum here. So this only works when I actually get a click here. Then I project onto a particular polarisation state, the polarisation told to me by the outcome of the measurement here, but it's non-deterministic. So do we have a deterministic source of these states? Well, we're getting there, but not really yet. So quantum dots are one way to produce single photon states. In recent years, they've improved a lot and are getting there, but they're still not deterministic. And there's still issues with making the photons the same all the time, basically. So this is an ongoing problem. So we see, in this sense, the continuous variables have an advantage because we have deterministic, high-quality sources of them, whilst we still don't really have that for single photons. So we could do another comparison, and that is to say, well, you know, if we want to incorporate quantum communication into the existing telecom setup that we have, because, you know, we use light to communicate classically, so maybe we can just plug these things into the telecom network and just keep going and start communicating quantumly. From that point of view, discrete variables don't work because our single photon sources and our single photon counters, that's nothing like what's in telecom systems. So they're telecom incompatible. On the other hand, coherent states and homodyne type detection are used in telecom, and so they're telecom compatible. So now we get another way in which continuous variables perhaps are more useful. Except now we want to extend how far we send our information. We don't want to just be within the local area. We don't want to just go 100 kilometres or so. We want to go, you know, to the next, you know, from Brisbane to Sydney, 1,000 kilometres or something like that. So we have to introduce repeaters. And now, unfortunately, you can prove that it's always true that repeaters are going to be telecom incompatible. There's no way to run repeaters in a way that is compatible with with what's the existing infrastructure is. So let's talk about what the centre is doing. So there is a number of programs in the centre, quantum communication programs in the centre, looking at various different approaches. So one is developing DV type protocols using generation 1 type repeater technology. And the innovation here is using rare earth quantum memories to both store and produce the photons. And so we have this very strong compatibility between the production of the single photons and storing them at local nodes while we do our processing, and maybe even processing them within the memories too. So you should hear a bit about that from Matt Sellers on Wednesday afternoon. We're also developing generation 1 repeater technology based on novel distillation techniques. And we'll hear about that from Sergei Slasarenko on Friday morning. I'll say a little bit more about that in a sec. And finally, we are developing continuous variable quantum communication tech and CV generation 1 and generation 3 repeaters. And you'll hear a bit about that from Neda on Thursday afternoon. So I had a bit of a spiel about, so five minutes? Okay, so I'll go quickly through this. So I sort of said, well, you know, the CV ones are always going to be telecom incompatible, and you might say, well, that wrecks all the advantages you were talking about with CV, but maybe not quite. So I'd just like to say a couple of words about why we're interested in continuous variable repeaters. One of them is that the CV technology may end up being more practical. As I said when I gave my generation 3 example, the logical qubit is going to be hundreds of modes, each one of them with a single photon in them, and in some massive entangled state that we have to like manipulate, whilst in principle using CV techniques we may be able to make logical qubits with many photons contained in just a single mode, which would be much easier to manipulate. So this is these cat states and GKP states. I'm sure you'll hear more about these probably in the quantum computation sense later on in the meeting. Also, CV technology may be more versatile. Just very rapidly, CV teleportation allows you to move any quantum state around, not just a quantum state that is specifically matched to your teleporter. And that's unique to CV teleportation. And so if you can build a repeater which distributes superior continuous variable entanglement, then you can use CV teleportation to move around any state you like, rather than just some specific type of encoding. So this may prove to be a versatile feature in the future. So very quickly, there are no quantum repeaters yet. Okay, so I'd just like to emphasize there's no generation 1, 2, or 3. They're just proposals. There's been lots of work on the basic building blocks going on for many years. There are some experiments where some of the building blocks are put together. And I just want to highlight again Sergei's talk on Friday morning, in which purification and swapping is put together. And for the first time, you can show that it actually works better than not doing it, in the sense that using this to get your entanglement over a channel is better than sending the entanglement just straight through the channel. So this is a very interesting milestone, I think. And with that, I shall stop and take any questions if I've got any time left.